In the previous section, we saw the effect of a solute on vapor pressure. Because changes of state depend on vapor pressure, solute presence in a solution will affect changes of state. They will affect freezing points and boiling points, or melting points and condensation points. Freezing point, boiling point, and osmotic pressure together are called colligative properties. These are properties which depend only on the number of solute molecules present and not the identity of the solute molecules. Colligative properties can oftentimes be used for determining molar masses. So again, the main colligative properties that we'll focus our attention on are boiling point elevation, freezing point depression, and osmotic pressure. Keep in mind that all of these properties depend only on the number, not the identity, of solute particles in an ideal solution. So first, let's look at boiling point elevation. The normal boiling point is the temperature where the vapor pressure of our liquid is equal to atmospheric pressure, in most cases 1 atmosphere. Non-volatile solutes decrease vapor pressure, which means it requires more heat to reach the boiling point at 1 atmosphere. Therefore, our boiling point is elevated. The magnitude of boiling point elevation depends on concentration of solute. For non-volatile solutes, we see that change in temperature is equal to this K value, which is mole boiling point elevation constant. It is a constant characteristic of a particular solvent times the molality of solute in solution. We see the same phenomena with freezing point. At 0 degrees Celsius, the vapor pressure of ice and pure water is equal. When a solute is dissolved in a solvent, the freezing point of the solution is lower than that of the pure solvent. With water, the vapor pressure of ice decreases more rapidly as the temperature decreases and eventually becomes equal to that of a liquid solution. The temperature where this occurs is our new freezing point. Freezing point will be lower compared to a normal freezing point. Again, this depends on concentration of solute in our solution. So our change in temperature is equal to our mole freezing point depression constant. Again, this is characteristic of a particular solvent times the molality of solute in solution. If we look at water, we can see in the red line the normal curve for water, where we have our normal freezing point and normal boiling points marked. The blue line represents a solution with water as the solvent, where we see a shift in our curve. The freezing point of our solution is lowered compared to that of pure water, and our boiling point is raised compared to that of pure water. Now, osmosis, our third colligative property, is the flow of a solvent into a solution through a semi-permeable membrane. The minimum pressure required to stop this flow of solvent across a semi-permeable membrane is equal to our osmotic pressure. Osmotic pressure in atmospheres is equal to the molarity of our solution times our gas constant times temperature in Kelvin. Osmotic pressure is very useful for determining molar masses because small amounts of solute produce very large changes in osmotic pressure. In osmosis, the semi-permeable membrane prevents movement of solute, so only solvent can happen. Only solvent can travel across the semi-permeable membrane. There's a similar process called dialysis, which happens at cell walls of plants and animals. In dialysis, small solute molecules and ions pass through membranes. This is actually the basis of kidney dialysis machines, which are used to clean blood. Now, solutions with identical osmotic pressures are called isotonic solutions. This is important in biological applications for fluid delivery. When cells are exposed to hypertonic solutions, solutions which have an osmotic pressure greater than that of the cell fluids, the cells will shrivel in a process called crenation. When cells are exposed to hypotonic solutions, where the osmotic pressure of the solution is less than the osmotic pressure of the cell, we get cell rupturing from water flowing in. This is known as hemolysis. There's also a process of reverse osmosis, which occurs when the external pressure is greater than osmotic pressure applied. The net flow of solvent will occur until osmotic pressure is equalized. Here the membrane acts as a molecule filter. This is the principle used in desalination of water to remove salt from seawater. Now again, colligative properties of electrolyte solutions depend on the total number of particles dissolved. For an electrolyte solution, keep in mind more than one particle is present. The relationship between moles of solute dissolved and moles of particles in solution is expressed by the Van Hoff factor, I, where I is equal to moles of particles in solution divided by moles of solute dissolved. These calculated values are based on an assumption of complete dissociation, which is not always true. Because of ion pairing, especially in very concentrated solutions, an observed I value may be less than a calculated I value. Here we have a list of expected I values for various salts. These I values are based on a complete dissociation of these various salts. Now, because of ion pairing in concentrated solutions, our observed I value may be different than an expected I value. As solutions become more dilute, the ions are further apart and less ion pairing occurs. However, ion pairing does occur to some extent in all electrolyte solutions. Ion pairing becomes most important for very highly charged ions at high concentration. We may have to include our Van Hoff factors in some of the equations we've seen, such as our change in temperature or osmotic pressure equations, to account for those ion pairings. Now, a colloid is a suspension of tiny particles in some medium. In a true solution, all particles are dispersed as individual solutes, and these particles are too small to scatter light. When individual particles become large or several small particles aggregate but no precipitate forms, we can get light scattering. When this light scattering happens due to this Tyndall effect, we say that we have a colloidal suspension or a colloidal dispersion. Suspended particles are single large molecules or potentially aggregates of molecules or ions ranging in size from 1 to 100 to 1,000 nanometers. We typically classify colloids by their dispersing medium and their dispersed substances. So we have things like aerosols, foams, emulsions, sols, which are sometimes referred to as sol gels, and then various solid forms of these colloidal suspensions. Colloids are stabilized by electrostatic interactions. We build small aggregates of oppositely charged particles, and since the outer layers have the same charge, they repel each other and don't form very large aggregates. Now we can destroy a colloid by coagulation. There are generally two methods to destroy colloids. We can either heat the suspension. The increased velocities cause ions to collide more often, and this then gives us some particle aggregation to form a large precipitate. Or we can add electrolytes. Adding electrolytes neutralizes the ionic layer, which results in the colloids being able to aggregate into much larger particles and eventually precipitate. This addition of electrolytes to neutralize ionic layers results in clays being deposited from river water at the mouth of the ocean.